Imagine a big tray of baklava, dozens of thin, golden layers of phyllo pastry, brushed with butter, filled with crushed nuts, and soaked in sweet syrup. From the outside, you only see the shiny top layer, glistening with honey and crisp perfection. But what if you could see every layer inside? All those delicate sheets of pastry, the nuts, and the syrup seeping between them without cutting it open. Well, that's exactly what the Optical Coherence Tomography, or OCT, allows doctors to do. Not with dessert, unfortunately, but with the eye. The retina is like a baklava, made of many ultra-thin layers, each with its own role. Some sense light, others color, others fine detail. OCT shines a special kind of light into the eye, and that light bounces back differently from each layer. Just like light would reflect off syrup, nuts, or pastry in a baklava. The result? A detailed image of every slice of the retina, all without a knife or a crumb. Now, let's trade our dessert fork for some physics. Optical Coherence Tomography, OCT, is an imaging method that lets doctors see the retina layer by layer, like taking a biopsy made of light. It's based on a principle called low-coherence interferometry, which measures how light waves interfere or mix after bouncing off different structures in the eye. A soft, infrared light beam, about 1.3 micrometers long, is split into two. One part goes to a mirror, or the reference arm, and the other part goes into the eye. When both reflected beams return, they combine again, but they only interfere if they've traveled nearly the same distance. This interference pattern tells us how deep the reflection came from. Each depth measurement is called an A scan. Thousands of A scans placed side by side make a B scan, which shows a detailed cross-section of the retina. Stack many B scans together and you get a 3D image. Early machines, called time domain OCT, had to mechanically move to measure each depth point, which was very slow and tedious. Modern Fourier domain OCTs, including spectral domain and swept source systems, analyze the light spectrum with a Fourier transform, capturing all depths at once. This advancement made OCT nearly 100 times faster and accurate within a few micrometers, allowing doctors to view living tissue in real time. Today, OCT can reveal every delicate retinal layer, helping detect eye diseases like macular degeneration or diabetic retinopathy long before symptoms appear. Let's return to our baklava. Each layer, the crisp phyllo, the nut filling, the sticky syrup, represents a layer of the retina, the tissue that captures light and sends it to the brain. Instead of slicing through the baklava, OCT uses light to slice through the eye, safely and painlessly. As the light passes from one layer to the next, some of it reflects, just like the golden shine of the phyllo pastry. Those reflections form interference patterns, which the OCT machine decodes to find exactly where each retinal layer begins and ends. The result is a cross-sectional image, a B-scan, a complete picture of the retina's internal structure, as if you could see all of the baklava layers from the side. So, just as baklava's sweetness comes from the harmony of its many thin layers, the retina's power lies in the precision of its own. And thanks to OCT, we can see every one of those layers. No crumbs, no syrup, just pure science. It's the perfect blend of physics, optics, and medicine. Quite literally, a dessert for the eyes.